Okay, let's start. So I will start by correcting something I said orally yesterday, but which is obviously wrong. I said that the event FA was not systematically equal to the event that you can pair the elements in A. I want to correct it. I mean, of course, it's wrong. I'm actually going to use exactly this equivalence. So exercise for you. So the three following properties are equivalent. So the first one is omega is in FA, meaning that every connected component of omega intersects an even number of elements of A. The second one is that there exists a subset, let's call it eta, smaller or equal to omega, so included in terms of subgraph, such that the boundary of eta is A. That's the second property. Remember, this means that this graph has odd degree at A and even everywhere else. And the third one is that there exists disjoint paths gamma 1, gamma k in omega such that gamma I, so edge disjoint, so that gamma I pairs, so that A is exactly equal to the endpoints of the gamma I. So you can pair the element of A by path in such a way that A is exactly the endpoints of all these paths. So these are equivalent properties. Okay, so today we are going to try to study the monotonic properties of the Fk measures and then try to deduce from it information on the Ising model. So this is maybe three monotonicity properties of Fk Ising. So in order to define monotonicity properties for the Ising model, it was monotonicity of spin-spin correlations. Here, it's going to be monotonicity in the following sense. So definition says that an event A is increasing. So A is included in 0, 1 to the E, is increasing if omega in A and omega smaller than omega prime implies omega prime in A. So here, smaller means in the sense of the natural order on 0, 1 to the E. Okay, so another way of saying is that an event is increasing if it is stable by adding open edges to my graph, by adding edges. Typically, there exists a connected component containing this and this point. There is a connection between blah, blah, and blah, blah. All of this is, they are increasing events. Okay, so this is my first definition. My second definition is to say that two measures, mu and nu, so consider a measure mu stochastically dominates nu, if for every A increasing, so for every increasing event, the probability of A under mu is larger or equal to the 1 under nu. Of course, you cannot ask that the probability of any event is larger or equal to the probability of the other one. Otherwise, it's, I mean, the only possibility is that you have a very, very trivial measure for the first one. But you can ask this for every increasing event. And that's what we call stochastically dominating. Notice the following is that if there exists, again, as yesterday, this part is really in my notes. So, I mean, for people who have hard time following, they can just open the notes. If there exists a coupling P such that, so I don't know, on pair of configurations such that, well, the first configuration is sampled according to mu, the second according to nu, and that systematically the first one is larger or equal to the second one. If you have such a coupling, then automatically mu dominates nu. Okay? Then mu dominates nu. By the way, here I would always write mu stochastically dominates nu like that. Okay. So why is it true, this? Well, let's just take mu of A. And let's write it using the coupling. So by definition, mu of A is the probability that omega belongs to A. Sorry, let's take nu of A. Omega prime belongs to A, right? The probability that the second coordinate belongs to A. But notice that omega is always larger or equal to omega prime. This is with probability 1. So here I can also add omega larger than omega prime. It's the same probability, right? But now if omega prime belongs to A and omega belongs to is larger or equal to omega prime, by reversing what I just wrote here, it tells me that omega is in A. So this is, I can add omega belongs to A, and therefore this is smaller than omega belongs to A, which is mu of A. It's a very, very simple observation, but I wanted to enter in your brain that if you want to prove stochastic domination, you need to construct such a coupling. And for people who already handle Bernoulli percolation, well, I encourage you to check that the coupling that normally you saw in your class is exactly a coupling having this property. Okay. So my goal is going to be to deduce monotonicity properties of the Fkg Ising model using, constructing couplings between different measures. And in order to do that, rather than always reconstructing the coupling, I want to give you a criterion that allows you to construct this coupling. And it's a very general one. It's actually not specific to Fkg Ising model. So proposition. So assume that for every edge E in my graph, and for every psi smaller than phi on the graph minus E. So I give myself two configurations outside E. If that now, assume that the probability that omega E is equal to 1, knowing that omega F is equal to phi F for every F not equal to E, assume that this is larger or equal to nu of omega E equal 1, assuming that omega F is equal to psi F. So what am I saying here? I'm saying that assume that the probability of being open for mu when you condition on the big configuration outside is larger or equal to the probability of being open for nu when you condition on the small configuration outside. Okay? Assume that you have that for any choice of E and any choice of these two configurations, the big one and the small one. If you have that, then there exists, then mu stochastically dominates nu. This is going to be a very good criterion for us because imagine, for instance, I'm working with the Fkg Ising model here. The probability of an edge being open condition on everything outside, well, by the domain Markov property that I described yesterday, it's going to be, and by the formula that I gave you, it's going to be equal to P or to P divided by 2 minus P. So it's going to be very explicit, and this type of criterion is going to be very easy to check in our case. Okay? Okay, so let's prove this proposition, and then after that, it's downhill. Yes?
Just one question, but it's the existence of a coupling on stochastic domination, it's equivalent, right? Or
Yes, it's equivalent. Yeah. Exactly. Okay, so how do we construct this coupling? Well, we are going to run a Markov chain. We are going to run a Markov chain on pairs of configurations in such a way that, well, the first configuration converges in law to mu and the second one to nu. Okay? So how will we run this Markov chain? First thing, we are going to start it, and we want to run this Markov chain, in such a way that the first configuration will always be larger or equal to the second one. Okay? So first thing we are going to do, we are going to start with the first configuration, which is the biggest one possible at time 0, meaning we are going to start with omega 0 equal 1, meaning the constant function equal to 1, and omega tilde 0 equals 0. Okay? And now we are going to run a dynamics, continuous time dynamics. So consider a continuous time Markov process constructed as follows. So you have exponential clocks on every one of the edges. And as soon as one rings, we are going to do something. And in order to do this, we need a certain, certain random variables. So certain random variables. So what we are going to do first is that you attach to each edge, well, a family of RID uniform random variable. Let's call them U, E, K. Okay, they are indexed by K and they are indexed by the edges. And now, and you already have exponential uniform and exponential random variables. So when when a clock rings, let's say it's at E and it's the kth time it rings at E. the kth time it rings at E. Well, if this happens, what you do is the following. You reset omega E and omega tilde E, and you reset them like that. I just want to be sure I'm not going to write something stupid.
Before you write it, I think that those U's are also independent EYs.
They are
Independent family of IID.
Yeah. What do you mean?
That EYs are independent.
Yeah, everybody is independent here. Like. Yeah, okay. Because they are in, I mean, okay, if you want like that, they are all in. Yeah, they are, everybody is independent, really. So omega ET is going to be equal to 1 if my uniform random variable is larger or equal to mu of omega E, or is say small, yeah, larger or equal to mu of omega E equals 0, knowing that omega on all the other edges is equal to omega f t minus for every f not equal to E. So what is omega t minus is just the configuration just before time t, just before the clock rings. Sorry. And 0 otherwise. And omega tilde et is the same thing with the same uniform random variable, but if nu with nu instead of okay? So if your uniform random variable is larger or equal to a certain thing, you put 1, otherwise you put 0, and you do the same with the second configuration, except for the second configuration. Even though it's the same uniform random variable, this parameter is different. Okay, this threshold parameter is different. So let's now meditate a little bit on this thing. First observation is that what is the probability of being open here for this new guy? Well, it's the probability of being larger or equal to that, meaning it's the probability to be equal to 1 knowing the thing. Right? Here it's 1 minus this probability. This guy is going to be larger or equal to this with probability 1 minus this, meaning exactly probability of being equal to 1 knowing everybody else. So from that, you see that this, mu is a stationary measure for this thing. So and I let you think about it, but it's kind of simple to see that by the finite energy property that I described yesterday, you can go from any state to any state infinitely many times in this thing. So the dynamics is irreducible. So what do I deduce from that? I deduce that there is a unique stationary state and that omega t converges in law to mu. The law of, let me write it like that. Okay? Same observation here with omega tilde, except it's with nu this time. So omega tilde t converges in law when t tends to infinity to nu. So what remains to check if we want to have a coupling between the two? Well, if we want to have a coupling between the two, we only need to check that omega t is always going to be larger or equal to omega tilde t, and then what we just do is we take the limit when t tends to infinity, and we have our coupling. So at time 0, it's perfect. I build it that way. Now, is it going to be preserved? Well, what I need to check is imagine that this is true up to time t minus, is it still true at time t? Okay, so here I need to check that if this guy is 1, then this guy will be 1. So I need to check, because I'm using the same uniform random variable, that this thing is larger or equal to this thing. Since omega t minus is larger or equal to omega tilde t minus, this is exactly the statement that I wrote here. Right? I mean, it's with 0, but I want this to be smaller or equal to this. So it's equivalent to that. So maybe I should have, I could have written it like that, and this would have been better, maybe. But, so the assumption guarantees that omega t is larger or equal to omega tilde t for every t, and so you simply let t tends to plus infinity to obtain the result. So maybe some of you already saw criteria of this sort, and maybe they saw another one which is equivalent, which is the Holy criterion. In some sense, I think when you stick to random cluster, this one is just very intuitive from the point of view of the dynamics that you are going to use to construct the coupling, and it's actually simpler to check basically than the Holy criterion. So we are going to stay with this thing.
Hugo?
Yes?
In your notes, you mentioned strict positivity for your reducibility.
Yeah. Okay. But here, yeah. Well, you are right. Yeah, well, okay. Okay, if you insist. So here, yeah, no. I don't like it. Let me ignore this. Yes. Obviously, it's with strict monotony. You want the thing to be reducible, but I'm really going to use it in a specific case where there it's. I agree with you. If you want it to be reducible, you need that. Okay. Good. So now, let's see how we apply that. So proposition, and these are three extremely important properties. So consider A and B increasing events, P smaller or equal to P prime, and Xi smaller or equal to Xi prime. Then I have the three following properties. The first one is the Fkg inequality. It tells you that phi gp psi of A intersected with B is larger or equal to the product of the probabilities. Which is exactly equivalent to probability of A knowing B is larger or equal to probability of A. So that tells you that conditioning on an increasing event helps the second one to happen, which is not very surprising since heuristically increasing events are events that lack open edges. So if they occur, that should push your configuration to be bigger. Second one is monotonicity. In P, meaning that phi psi g p prime of A is larger or equal to phi psi g p of A. And there you recover these two properties. They are really like you recover those that you have for Bernoulli percolation, for instance. This is really some classical property. And the last one is the comparison between boundary condition and it says that phi psi gp of A or phi psi prime gp of A is larger or equal to phi psi gp of A. So it tells you that the bigger the boundary condition, the bigger the probability of A. And this one is obviously true for Bernoulli percolation, since in this case you don't care about boundary conditions. But here it's going to be fundamental. It's absolutely crucial to have a property like that to handle the lack of independence in your model. Maybe we need to use a little bit of water because I'm pushing more and more the dust away, but it's coming back. Okay. So how do we prove these properties? Let's start with these two properties. They are much simpler in some sense. This one, for instance. So we need to check that if I take psi smaller or equal to psi prime, if I look at phi psi gp prime of omega e equal 1, knowing omega f equal psi f for every psi prime f for every f not equal to e, I want that this is larger or equal to phi psi gp of omega e equal 1, knowing omega f equal psi f. Okay, this is equal to what? Well, we said this is equal to either p prime if x is connected to y in psi prime, or p prime divided by 2 minus p prime if not. Here I said that this is equal to p if x is connected to y in psi, and p over 2 minus p if x is not. So the only thing that remains to be checked is that since psi is smaller or equal to psi prime, and p prime divided by 2 minus p prime is smaller than p prime, here you automatically always get that this guy is smaller than this guy, right? Even simpler, if you have this like that, then here you get this. And here, sorry, I should have said it was really in this thing, right? In the boundary condition, which is a union of the two. And so here, if you have boundary conditions instead of this guy, then it's like that. But a fortiori, if psi is connected, if x is connected to y in psi union psi, x is connected to y in psi prime union psi prime. Okay, so you get, in both cases, it's completely trivial. So remains only to check the Fkg inequality. And this one, I want to leave it to you as an exercise. So there are two things that you need to be careful there, is that you need to define the measure condition, compare the measure unconditioned with the measure condition on B. And you need to check indeed exactly what Sébastien was mentioning, that just before I use the positivity to guarantee that my dynamics was irreducible. And here, if you think about it, if you take the measure condition on B, it's not irreducible, it's not positive anymore, simply because it gives positive weights only to guys that are in B, right? But check that when you run the dynamics, there is no difficulty. Okay, so exercise. Again, it's a good exercise to check that you understood the rest. Prove Fkg. Okay, so these are the monotonicity properties of the Fk Ising model. And notice one thing there, remark. If you set, say, A equal F, so if you apply to FA and FB. I mean, I realize that maybe A and B here I should have used E and F, not to collide with this notation. But if you apply to A being this event and B being this event, the first inequality, the Fkg and sec psi equals 0 or 1, the first inequality translates into what? Somebody is doing like that because I'm again saying something wrong? Oh, well, no, not really. Come on. Yes, but so it translates into that. And this is 0 or 1. And here, if these two things occur, what do you deduce? You deduce that f of A symmetric difference with B occurs. So this translates into sigma A, sigma B, either in free or in plus, is larger or equal to sigma A, sigma B. So we recover, in this special case, we recover the second Griffith inequality. Okay? This one, what does it translate to? It translates to sigma A, so phi GP of A larger or equal to phi G, I mean P prime of A larger or equal to this. It translates into sigma A G beta prime larger or equal to sigma A G beta for any beta prime larger or equal to beta. So you recover the monotonicity of spin-spin correlations from the monotonicity in P. And here, for the last one, for the boundary conditions, observe that you obtain, for instance, that phi 1 GP of A, of FA, sorry, of FA larger or equal to phi 0 GP of FA, right? The one boundary condition is larger or equal to the 0, 1. This gives sigma A G beta plus larger or equal to sigma A G beta. So the plus boundary conditions for the Ising model are bigger than the free one. Yeah, I should not put a 0 here. Okay? So there is a direct, again, here using the Edwards-Sokal coupling, there are direct implications for the Ising model. Okay. Speaking about applications, now let's go to infinite volume measure. So infinite volume measures. So my goal in this section is to define infinite volume version of these measures, and in particular to deduce that the free state, so the zero boundary condition and the plus and the wired boundary conditions, are in fact equal most of the time. And this will translate into the fact that the free measure for Ising is equal to the plus measure for Ising most of the time. So theorem, let me check that. So proposition, there exists two measures let's call them phi 1, phi 0 p and phi 1 p, such that two measures on 0, 1 to the edges of ZD, such that for every event A depending on finitely many edges, we have that the limit when n tends to infinity of phi 1 or 0 lambda n p of A is equal to phi p 1 0 of A. So these measures, there are two measures that are limits, weak limits of the measures in finite volume. I understand this is not super exciting, but don't worry. I mean, we are going to have two cool theorems in 15 minutes. But if I was told that if I don't define objects, then people complain. So that's your fault, not mine. I can directly go to the cool problems, but. Okay, so let's prove that. And by the way, everything I'm going to do here, it's interesting if you try to do it for Ising directly, because in fact I could have done it for Ising. Just try to run exactly the similar arguments for Ising. Okay, so I'm going to do it for phi 1. No, for phi 0, say, and it's the same for phi 1 anyway. So the idea is that in order to have the property there, because any event depending on finitely many edges is inclusion-exclusion, I mean, can be written as the inclusion-exclusion of increasing events, and for people that are bored, you can try to prove this fact. Then it's sufficient to prove the convergence only for these increasing events. Okay, so fix A increasing depending on finitely many edges. Okay, and now the observation is, imagine, I mean, let's try to compare the probability of A when I look at the box of size n plus 1 to the probability of A when I look at the box of size n. And I suppose that finitely many edges, say, in lambda k. And now I take n larger or equal to k. So if A depends only inside the box, I mean, of edges inside the box of size k, this thing, I mean, A doesn't depend on any edge which is outside the box of size n, so I can condition on all the edges outside the box of size k. N, sorry. So this is just the conditional expectation of lambda n p of A, knowing omega in lambda n plus 1 minus lambda n, where by this I mean the edges of lambda n plus 1 minus the edges of lambda n. Okay? But by definition of the domain Markov property, this is phi, let's call it psi n, or I mean omega restricted to lambda n plus 1 minus lambda n of A. This is the domain Markov property that gives me that. Okay. But now here, these are some boundary conditions. I don't know them very well. But what I'm certain about is that those boundary conditions are larger or equal to the zero boundary conditions, because the zero boundary conditions are the smallest one. So this is larger or equal to phi 0 lambda n plus 1p of phi 0 lambda n p of A. which is exactly phi 0 lambda n p of A. So this is by comparison between boundary conditions. So what did I just prove? I proved that this sequence is decreasing, and exactly like what I did for the Ising model, that implies that the sequence converges. Okay? As a consequence, phi 0 lambda n p of A converges. And just the fact that in finite volume those are measures, it converges to something which can be understood like, which is coherent to construct an actual measure. So it converges to a value denoted phi 0 p of A, and just the consistency in finite volume enables to extend this function phi 0 p, which is defined only on finite, on increasing event depending on finitely many edges, to extend it to any finitely, to any event depending on finitely many edges, and therefore to all events in my sigma algebra. And that's the end of the proof. Okay. So it's not, in some sense, it's exactly the same proof as for Ising. But it's what we are going to do next, which is going to be a little bit more specific. So, second proposition in this section, phi 0p and phi 1p are invariant under translations and ergodic. Ergodic meaning that any event which is invariant under translation has probability 0 and 1. And there already, this is not true for the free state of the Ising model. So there already there is a big difference between Fk and Ising. Okay. So let's try to prove it. Let's say for phi 1, and you can try then to prove it for phi 0. So for phi 1, invariance of the translation is going to simply follow from the following fact, which is that if I look at phi 1 lambda n p of tau x times A, where x, tau is a translation by a unit vector. If I can do it for translation by any unit vector, I just have it by composition for every translation. And this, if I am in finite volume and I'm looking at the translate of my event A, so this is A and I look at the translate of A, then it's really exactly the same as looking in tau lambda n p. Actually, it's, yeah, of the event A. It's like translating the box by the same guy, right? You are in your A if your translate inverse is in, you are in tau A if the translate inverse is in A, and that exactly corresponds to that. But this, you see, is clearly larger or equal, smaller or equal, sorry, to phi 1 lambda n minus 1 p of A, and it's clearly larger or equal to phi 1 lambda n p of A. Lambda n plus 1. Why? Because I should have done it for 0, but okay, that's actually a good example. Lambda n plus 1, lambda n minus 1 is included in tau lambda n, and lambda n plus 1 is containing tau lambda n. If I would have done that with a one boundary condition, I would have had that the probability here is smaller or equal to the probability here, because this is a smaller graph, and the probability here is larger or equal to the probability here, because this is a bigger graph. The farther the one boundary condition, the smaller your probability. It's exactly the opposite of the free one. Okay, but both things converge as n tends to infinity to phi p1 of A. And this thing converges to phi 1p of tau A. Therefore, the two are equal. Let's prove ergodicity now. So in order to prove ergodicity, since we are working with a sigma algebra where by definition every event can be approximated by events depending on finitely many edges, ergodicity follows from mixing. So since every event can be approximated by events depending on finitely many edges, ergodicity follows from mixing. From the mixing, which, just to recall everybody, means that for any event A and B, depending on finitely many edges, and for any translation, if I look at phi 1p of A intersected with tau to the k B, well, this converges as k tends to infinity to phi 1p of A times phi 1p of B. Okay? If I just translate my event more and more and I look at the probability of the intersection, it converges to the product of the probabilities. And notice that A and B depending on finitely many edges. Okay. Notice that this property, just by inclusion-exclusion, I can simply prove it for increasing events. It's sufficient. Okay? So let's try. So we focus on increasing events. Okay, so first thing is that this thing, well, by Fkg is larger than the product of the two events because there are two increasing events. And by invariance under translation, I get this. So at this point, one of the inequalities is completely trivial. And I need to focus on the other one. To get the other one, well, I'm just going to write it as phi 1p of b times, or tau kb, times phi 1p of a knowing tau kb. And notice the following. So you have A, which depends on edges there, and you have B, that depends on edges there. So B, if I condition on B, I condition, say, in a configuration in B, it induces boundary condition on all the edges which are not depending on these, which are not there, right? So in particular, if I take the box here of size, say, k over 2, it induces, conditioning on B induces random boundary conditions on the boundary of lambda k over 2, right? By the domain Markov property. But those boundary conditions, they are necessarily bounded. They are smaller than the wired boundary condition, that the one boundary conditions, right? So this whole thing here is smaller or equal to phi 1 lambda k over 2 p of A. Okay, this thing converges, this thing is equal again to this, and this thing as k tends to infinity converges to phi 1p of A. So again, this thing is smaller or equal to phi 1p of A times phi 1p of B. Notice that it's really going by two inequalities, since here we have the comparison between boundary condition happening. So it's not an equality, of course, these two things. The random boundary condition induced by the event B are tricky a priori, but they are always dominated by the wired one. Okay? Try to do it for the zero state. There is one small trick, and once you have seen it, it's fine. Okay. So from that, we have constructed infinite volume measures. And they are ergodic and invariant other translations. So just a remark at this stage, which may be useful. So we have the Edwards-Sokal coupling in finite volume. Good. Can we construct an Edwards-Sokal coupling in infinite volume? Because we have this plus state that we constructed and this free state that we constructed for the Ising model. We have the phi 1 and phi 0 that we constructed for Fk Ising. How can we relate them directly? Well, they are both, they are all limits of the finite volume states for which we have the Edwards-Sokal coupling. So you can just take the limit of these couplings. And what will you end up with? Well, you end up with the following coupling, which is that phi 0 and these states are coupled just in the natural way. There is no trick. You just color every cluster at random plus or minus 1, no problem. So these are coupled by coloring clusters at random uniformly. And notice that here, even infinite clusters, no problem with it. But be careful that if you have 3 different infinite clusters, you color them in a different way in this case. You really color them like each cluster has a different thing. Now phi 1 p and these states are coupled in a fairly intuitive way, but I really want to state it, which is are coupled by coloring any finite cluster at random uniformly, and by giving plus to all infinite clusters. Clusters meaning connected components, sorry. Okay? So here's the trick, and I really want to highlight it, is that here if you have several infinite clusters, they receive like different plus minus spins. Here all the infinite clusters receive plus spin. In the case of in the case of ZD, we are going to see that actually there is not a huge difference because the infinite cluster is unique. That's what we are going to see. But this will make a huge difference if you are, say, on a tree, for instance, or on very big graph. For people who like non-amenable groups, I mean, this is really a very, very different procedure. And in particular, it explains why on this huge graph, for instance, the free state is not related to the plus state whatsoever. Okay? You are going to see that here we are going to prove that it's often related on ZD. Also, that observation here explains a little bit why this state is not always ergodic. It's always the case for phi 0. It's not always the case for this free state. Why? Because there is some information that is going at infinite distance. It is the sign of your infinite clusters. So if you don't have infinite clusters, then in fact you can deduce that this guy is ergodic, just from the ergodicity of phi 0. But if you have an infinite cluster, which will happen actually for every p larger than pc, we are going to see that in a minute, so for any beta larger than beta c, then you have an infinite cluster, therefore you have a lack of ergodicity, and this guy is not ergodic anymore, and we will prove next week that in fact it's just the average of the plus and the minus states. But this will require an actual proof. It's not going to be easy at all. It's a fairly recent result even. No, this special case maybe not, but classifying in general is a fairly recent result. Okay, so that was the fourth. Let's go to the fifth section of this lecture, of this, which is to try to answer this thing that we said yesterday that Balint noticed, and where I told you that I was cheating, is why would it be that for beta larger than beta c, the spin-spin correlations do not decay? So here I'm going to call it, it's like relating long-range ordering, which is this property that the spin-spin correlations do not go to 0 for the free state, to positive magnetization, which is the way I define the critical points. So long-range ordering against spontaneous magnetization. Okay, so spontaneous magnetization is going to be the property that m of beta, which is just sigma 0 plus beta, is strictly positive. That will be my spontaneous magnetization property. And my long-range ordering property will be that the limit when x tends to infinity of sigma 0 sigma x beta is strictly positive. Or let's say the infimum on x in ZD of sigma 0 sigma x beta is positive. Okay. So let's try heuristically to see why or why not, in some sense, why these two properties should be equivalent or why they shouldn't be. Okay? What can go wrong? And in order to understand how these two properties are equivalent, Well, let's try to translate via our Edwards-Sokal coupling these properties into properties of the measures phi 0 and phi 1. So the first one here, sigma 0 plus beta. Remember, sigma 0 in the Edwards-Sokal coupling with plus boundary condition, sigma x, the average of sigma x is just a probability that x is connected to the boundary. And here in this infinite volume version, it's the probability, well, that x is in an infinite cluster, right? So this is phi 1p. Always beta and p everywhere, I think you understood it, are related by this p equal 1 minus e to the 2 beta. So here, I'm going to denote it like that. It means 0 is connected to an infinite, it's connected to infinity. Okay? The long-range ordering, well, sigma 0, sigma x beta. Well, if I go back to this, well, 0 and x needs to be in the same cluster. So phi 0p of 0 connected to x. So what can go wrong there? Well, intuitively, nothing, right? Intuitively, here it's saying there is an infinite cluster. So if there is an infinite cluster, and you think it's a huge one, then whatever the distance between 0 and x, well, the 2 points may belong to this infinite cluster. But when I'm saying there is a huge one, I'm assuming something which a priori is not trivial, is that in some sense I have a unique infinite cluster. So first thing I need to check is, do I have uniqueness of an infinite cluster, of the infinite cluster? If I have that, indeed by ergodicity, this infinite cluster is going to be everywhere, and 2 points will have positive probability of both being in this infinite cluster uniformly in the distance between the two. But there is a second thing that I really swept under the carpet when I told you this is a sufficient analogy between the two, is that, phi 1p has no reason whatsoever to be equal to phi 0p. A priori, they are completely different. So phi 1p, is it equal to phi 0p? If indeed phi 1p is equal to phi 0p and there is a unique infinite cluster, then by ergodicity it will be simple to deduce what we want. Actually, it will be even simpler than by ergodicity. If there is a unique infinite cluster and that phi 1p is equal to phi 0p, if I want to prove that this implies this, I would just use that 0 and x connected to each other is an event which is easier to achieve than 0 and x connected to infinity. These are two increasing events, so it's larger or equal to the product of the probability that 0 is connected to infinity times probability of x connected to infinity, and this is sigma 0 plus beta squared, right? I will rewrite this anyway later. But this small discussion is to argue that, to motivate you to try to prove these two properties. This one is going to be not so easy, in fact, but at least this one. Notice that in order to make what I claimed yesterday, I only needed that these two properties are equivalent for almost every beta. I didn't really need it for every beta. We will prove that it's true for every beta. This will be one of the lectures next week. But today I'm going to focus on trying to prove this for almost every p. Okay? So let's start by this today. Then I think, just not to rush too much, we will do this on Monday. Or at least maybe we will start today and finish. So first theorem. probably going back to Leibowitz, even though it was stated in the case of the Ising model, but you can recast everything in the, you can recast this property in the Ising model. This one not, but this one yes. So it's saying that the set of values of P for which phi 0p is not equal to phi 1p is at most countable. Again, we will actually prove next week that it's empty. But this is much harder. So it's at most countable. And here, when you see at most countable, what are the type of properties that give you that a set is at most countable? Well, one of them is to look at the set of points for which a convex function is not differentiable, for instance. The set of points for which a convex function is not differentiable is at most countable. And that was the way Leibowitz did it. He used what we call the free energy, which is a very important tool in statistical physics in general, which is a convex function, and he proved that except at the places where it's not differentiable, phi 0 must be equal to phi 1. The reason why a convex function is not, there are only countably many points for which a convex function is not differentiable. The reason is that, well, its derivative cannot be discontinuous in at most, cannot be discontinuous in more than countably many points. Right? The derivative is an increasing function. It's a classical small exercise to check that an increasing function has at most countably many discontinuity points. Well, I'm going to use actually this. So I'm not going to prove to you, I'm not going to use the Leibowitz argument. I'm going to use a new one, which I think in some sense it's really relying on the same idea, but it's much shorter. So, shorter is better. Okay. So instead of looking at the free energy, we are in fact going to look at its derivative, which is the probability of being open. So first step, and this is required in both cases, in Leibowitz proof and in this proof, is to say, okay, if phi 0p of omega e is equal to phi 1p of omega e, then phi 0 is equal to phi 1. So this is a sufficient condition to get the equality. And in fact here, you can even say if this is larger or equal to this, because the other inequality is trivial. Okay, how do we prove that? Well, we are going to use the coupling. We have an increasing coupling between phi 0 and phi 1, at least in finite volume. Right? Well, if we have this coupling and that the density of the edges is the same, that means that almost surely none of the edges will be open in phi 1 and closed in phi 0. But that means, because anyway, all the edges that are open in phi 0 are open in phi 1, that means that it's exactly the same set of edges which is open in both things. So I'm just going to translate that. Last year I did it in finite volume and people complained, so I'm going to do it directly in infinite volume. Let's assume you have a coupling in infinite volume, which you can take by just taking the limit in the infinite volume. So then you take an event A. So let A be an increasing event, say. And let's look at phi 1 p of A minus phi 0 p of A. And let's say this is the probability in my increasing coupling that omega 1 you understand what I mean by that. That's the marginal which has low phi 1 is in A, but omega 0 is not in A. But since omega 1 is larger or equal to omega 0, and I'm looking at an event which is increasing, this can occur only if there exists somewhere an edge which is closed here and open here. So this is smaller or equal to the sum over every edge in ZD of the probability that omega 1e equal 1 and omega 0e equals 0. You need to have an edge like that, otherwise this doesn't occur. Okay, but this is just phi 1 p of omega e minus phi 0 p of omega e. So this is smaller than sum phi 1 p of omega e minus phi 0 p of omega e. Since these things are equal, it gives me 0. It's a very simple argument. I just wanted to spell it out completely. Because if you try to do the same, for instance, with Ising directly, it's a little bit more tedious. It's not like it's the end of the world, but it's less transparent, I think. Where again, transparent is a very subjective vision, I guess. Okay. That was step 1. Second step is that if that phi 1p of omega e equal phi 0 p of omega e at every continuity point of the map, P gives phi 0 p of omega e. So if I am at a point where the function is continuous, or I put phi 1, so maybe I don't want to. No, phi 1 p of omega e. This concludes the argument since this function is increasing, I mean it's non-decreasing, so it has at most countably many disconnected points. Yeah. Okay, so how will I do that? So let's pick, let's assume, so we fix a continuity point, okay? And consider P prime, so fix P a continuity point. And assume that, in fact, and set A to be phi 0 p of omega e, and B, which is phi 1 p of omega e. Okay? So notice, right, that A is smaller or equal to B. Now fix also epsilon. Think of epsilon very small, okay? In particular, for instance, smaller than 1 minus A and smaller than B, say. Okay. So first observation, I'm going to set my proof in a box of size n. First observation is that the phi 0 lambda n p of the sum of omega e, so of omega, the number of open edges, the expected number of open edges for this measure, well, by comparison between boundary condition, it's smaller than it's smaller than the number of edges in my box times phi 0 p of omega e. So it's equal to, it's smaller than that, so it's smaller than E of lambda n times A. Right? This is just the sum over the edges of the average probability of being open. And because I'm in lambda n with free boundary condition, it's smaller than free boundary condition at infinity by monotonicity. Same thing, phi 1 lambda n p of omega Well, by definition, this is larger or equal, by comparison between boundary conditions, it's larger or equal to this. These are two trivial observations. But notice that these two trivial observations, they imply the following thing. They imply that the probability that you have fewer than a minus epsilon, a plus epsilon, sorry, times e of lambda n open edges in my thing, this is larger or equal to epsilon. So if you have something of average lambda n times a, which is bounded between 0 and lambda n, the probability that it's smaller than a plus epsilon lambda n is larger than epsilon. It's Markov. And same thing, phi 1 lambda n p of omega larger than b minus epsilon e of lambda n is larger than epsilon for exactly the same reason. Okay? So this can look weird, but it's just saying you have a certain average, right? It's not super surprising that the probability that you are fairly close to your average is large. Here I'm just proving that in the cheapest way possible, which is just using Markov. There would be tons of other arguments to tell you that much stronger results than that are true. This is very close, the probability is very close to 1 by concentration and so on. I just want the cheapest argument to get this scheme. Okay. Well, we are basically done. So fix lambda to be equal to, so now, we are going to pick a p prime, which is larger than p. So pick p prime larger than p, and set lambda to be equal to p prime 1 minus p divided by p 1 minus p prime. Okay? And this is larger than 1. Okay. So there we prove the following. This was a b minus epsilon e of lambda n. Right? That's what I proved there. But therefore, this is a fortiori true if I put a p prime here. Simply because p prime is larger than p. Okay. But now here, notice the following. How can I compare phi 0 to phi 1? What is different in phi 0, in the definition of phi 0 and phi 1? It's the way I'm counting clusters, right? In phi 1, I'm counting the cluster as all being 1 when they touch the boundary, while it's not the case for phi 0. But therefore, how can I relate this phi 1 to phi 0? How can I relate both? Well, for the numerator, the 2 to the number of clusters is smaller here than here for the same configuration, right? In the denominator, it's smaller, and it can be much smaller, but not by more than 2 to the size of the boundary, because that's the maximal difference between the number of clusters possible. So if I want a bound here, I can put 2 to the size of the boundary. If I put 2 to the size of the boundary, I'm certain to be able to compare the two quantities, right? What is going to be crucial is that this is of the size exponential of the size of the boundary. Okay? So now we are with phi 0. So here, I'm going to put an additional thing. I'm going to lose something more. I'm going to simply pick the same thing here. And I'm going to divide by phi 0 lambda n p prime of omega smaller or equal to a plus epsilon times e of lambda n. Okay, I'm just divided by something smaller or equal to 1, so I'm still increasing things there, right? You are going to understand in a second why I'm doing that. I mean, in 3 seconds, the time that I'm just... Because this thing, in fact, is quite small. Why? This is this thing. So here, it's the ratio of two things, right? It's the ratio of the sum over every configuration omega with the indicator function of this event divided by the partition function. And here is the sum over every configuration omega with this thing happening divided by the partition function. So the partition functions, they cancel each other. But now the sum over the omega having this property, so okay, let me add really one more line. Sum over omega of p divided by 1 minus p to the number of edges, 2 to the number of clusters, and here I get an indicator function of the number of open edges larger than b minus epsilon e of lambda n. And I need to divide by the same thing, p over 1 minus p to the omega. These are p prime, right? What did I do? Oh, sorry, I forgot one line. Oh, actually, I can do it now. Okay. I was a little bit lucky on this one. Okay, it's like that. Okay. This guy is still here and will remain up to the end. So now here, notice that if I introduce lambda, I can express this thing, I can replace by p here, and put a lambda to the number of edges here, and lambda to the number of edges. Right? Yes. But notice that here, you always have more than b minus epsilon e of lambda n edges. And here you always have fewer than a plus epsilon e of lambda n edges. So this lambda to the omega, why is it not smaller than 1? Ah, no, it is smaller than 1, sorry. Here, because you have more than that, this is always smaller than lambda to the b minus epsilon e of lambda n. Because p prime is obviously smaller than p. Okay. Again, you know, you are bound to this plus minus and larger or equal, smaller or equal. It's much simpler to prove theorems like that. Yes, sorry about that. I definitely hope it has to be smaller. Yes?
Your first inequality, when you went from p to p prime,
Yeah.
you increased.
No, because I didn't increase because, I mean, okay, it's catastrophic. Things are catastrophic. Please do not run. I mean, run in 5 minutes, but okay, yes. You still love me, right? Okay. It doesn't change much. Kind of. Okay, here on the opposite, lambda is, I mean, omega is smaller than a plus epsilon e of lambda n. So I get a plus epsilon e of lambda n. Okay? And now I get the ratio without this guy, the ratio of these two things. But this is exactly going back to this. It's exactly the phi 0 lambda n p of omega larger or equal to b minus epsilon en divided by phi 1 lambda n p of omega smaller or equal to a plus epsilon e of lambda n. Right? So at this stage, things look moderately good. I mean, already a little bit better than before, but here we have a term which is of order of the boundary. Here we have a term which is b minus a minus 2 epsilon of e of lambda n. And notice that if b is larger than a strictly, I can choose epsilon small enough that this is of the order of volume, which is bad. Which is much smaller than this. And here, what do I have? This thing could be bad, but this is smaller or equal to 1. That's 0. This is smaller or equal to 1. And this is, well, it could be tiny, but, well, it's not, because that's this guy. So it's larger or equal to epsilon. So all of this is smaller or equal to 1 over epsilon. Okay? So what did I just prove? I proved that epsilon squared was smaller or equal to 2 to the lambda n times lambda to the b minus a minus 2 epsilon, size of lambda n, basically. Okay? Like d times this, or, okay. Let's lambda is strictly smaller than 1. So what is the only possibility here is that b is larger or equal, is smaller or equal to a plus 2 epsilon. So this implies that b is smaller or equal to a plus 2 epsilon. Right? Yes. Yeah. B has to be smaller or equal to a plus 2 epsilon. And this for every epsilon. So that implies that b has to be smaller or equal to a. So what did I just prove? I took p prime smaller than p, and I proved that for any p prime smaller than p, the probability of being open for the wired boundary condition, for the one boundary condition, is smaller or equal to the probability of being open for the free boundary condition above. Right? So this is exactly equivalent, like by the definition, to phi 1 p prime of omega e smaller or equal to phi 0 p of omega e. So for any p prime smaller than p, we have this inequality. But if you are at a continuity point for p, this thing is converging when p prime tends to p to phi 1 omega p. So that implies, so we have phi 0 p of omega e, which obviously is smaller than phi 1 p of omega e. But by letting p prime tend to p, phi 1 p of omega e is also smaller or equal to phi 0 p of omega e. Okay, so I apologize for this p prime thing. It has been a long time I didn't present this proof. But let me summarize the argument. The only thing you need to prove that phi 1 p of omega e is equal to phi 0 p of omega e, you need to prove that if you take a p prime smaller than p, even for the big measure, so even if you give all, like you help as much as possible your measure, the probability of being open is smaller or equal to the probability of being open for the larger parameter p. So how do you do that? You just fix your p prime smaller than p. You say at the value of p, the probability of being smaller than your average plus epsilon is larger than epsilon. At p prime, the probability of having more edges than b minus epsilon times your average is larger than epsilon. And then here, you just use, if you want, the Radon-Nikodym derivative between the two measures and the fact that they differ only by a boundary, exponential of the boundary type quantity to prove that this cannot occur, that you have something constant smaller than your Radon-Nikodym derivative between phi 1 and phi 0 times, if you want, your Radon-Nikodym derivative between phi 0 p and phi 0 p prime, or phi 1 p and phi 1 p prime. And you use that this is of the order of volume instead of order of boundary. I mean, this proof, I think, is much simpler than the original argument, even though it's writing exactly the same thing. I mean, it's the same idea, it's just going directly without the free energy. Okay, this is the end of this lecture, and on Monday we start with Burton-Keane argument, and there is a question.
I have one question.
Yes.
So the spontaneous magnetization you define as the magnetization with the plus boundary conditions in the thermodynamic limit. But there is another one, another definition usually accepted, namely that take a symmetry breaking external field, take the thermodynamic limit down to zero in the breaking field.
Yeah, that's the same guy.
So that must be, that gives the same guy.
Yeah.
But how, so this type of proof works for that too? So if I forget about this one and I take that spontaneous magnetization.
No, there you just need to prove that the state with H positive, so with the external field, converges when H tends to 0 to the plus state. But this is much simpler than that to do.
So it converges to the plus, so that's the proof with...
This is always true, whatever the graph and so on, so this is less delicate. Here, for instance, I did use something very important, which is I did use that the size of the boundary is much smaller than the size of the volume. So on a tree, for instance, this argument doesn't work, and it's normal because actually it's not true, the claim. So I use amenability. What you are saying with the positive magnetic field and how it converges to the plus states, this is true whatever, regardless of the graph. Yeah, so it's a different argument. Okay, well, thank you and have a nice weekend and go France.